Okay. Chapter 10, Exponents and Logs. This is fun stuff. Like everything we do is fun stuff, but it's fun stuff, and it's importante fun stuff. Okay? Because, yeah, it's importante. Okay. Exponents and logs. So if we say 10 cubed, that's an exponential function. Exponential. And the 3 is the exponent. Okay? Math is really quite a simple thing, yes? So we write 1,000. What's 1,000? Well, this is the ones. That's the tens. That's the 100s. And that's the thousands place. Why? Well, this is 10 to the 0 power. That's 10 to the 1th power. That's 10 to the 2th power. And that's 10 to the 3rd power. Okay? So 10 to the 3 is 1,000. We write that out. And all that says is there's 1 10 to the 3rd in that number. And 0 10 to the anything else's. Pretty darn exciting and tootin' and all that, yes? So this is the base. So we do math in base 10. We don't write base 10 out because we all know we do math in base 10. If we were one finger short on each hand, we might do math in base 8. And in fact, among the many things that happens in the computer world is we do math in base 8, octal math. Okay? In fact, I know you're bored. Yep, I screwed that up. Ignore that. Okay, this is a math joke. A math joke? No, you didn't think there were such things? Yes, there are. So December 25th and October 31st, that's Halloween and Christmas, right? Except that what we're saying here, des is short for decimal, so that's base 10 25 equals octal, which is base 831. You're like, wait a second. So let's think about base 8. 31 in base 8. Well, let's do 1,000 in base 8. 1,000. That little 8 down there means base 8. That would be 8 to the 0. That would be 8 to the 1. That would be 8 to the 2s. And that would be 8 to the 3s. So what looks like 1,000 to us in base 10 is 256 in base 10. Okay? So all you computer nerd people, you know, for example, that very often you run into numbers like 256 or how many bytes in a megabyte? And don't say a million, because that's wrong. Computer stuff is done in base 8 or base 2. Okay. Is that exciting? So let's try this experiment. 256 times 4 is 1,024. So when you see KB in computers, because base 8, when you see KB in computers, you're not actually getting 1,000, you're actually getting 1,024. Yeah? So a megabyte is that many bytes. Okay? In the computer biz, we write out numbers like this. That's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7th. Okay? Yes? 2 to the 5. No. 2 to the 5 is 2 times 2 times 2 times 2 times 2 is 32. 2 to the 7th is 128. So that in base 2 is 160. Yeah, is that exciting? Okay. Capital A in computer talk is 65. Yes? Which is 1. That's 2 to the 0, which is 1. And 2 to the 6th, which is 64. 1 is 65. 100001 is 65. Okay? And you're like, I'm never going to use that, but it's important to understand how these exponents work. Okay? So, the opposite of an exponent is a logarithm. No? Yeah. The opposite, and we can say log, or we'll talk about natural logs here in a minute. But we'll get back to this. Okay? So it's logarithm, but I'm not likely to ever say that word. It's log. Log. Okay? So 10 to the 3, the log of a number is just its exponent at that base. So the log base 10 of 1,000 is 3, because 1,000 is 10 to the 3rd. The log base 10 of 100 is 2. Log base 10, let's get rid of that. We don't need those there. Log base 10 of 100 is 2, because 10 squared equals 100, and that 2 is going to be the log. It's so exciting, right? So this is the logarithm. And you're saying, why do I care? Well, we deal with these things. The trick is we're going to deal with logarithms. We're going to deal with exponents and logs to deal with growth things. Okay? So if I draw a graph, and here's time from the beginning of time, and the population of the planet Earth, what's that graph look like? Well, it looks like that. Okay? If I want to get statistical with that graph, it's painful. It's painful because there's not much, and then all of a sudden, boom. Okay? A graph of the stock market looks kind of like that over time, that it's okay? Logs can take this, and we'll talk about how this works, but think about it now. 10, 100, 1,000, 10,000, 100,000. So if I graph those 5 points, 1, 2, 3, 4, 5, okay? So if I take 1, this is 10 to the 1, 10 to the 2. So if I take 1, I get 10. If I take 2, I get 100. If I take 3, I get it's already off the scale, right? So if I graph this, I'm going to get right? But if I take the logs of this, log is 1, it's 2, it's 3, it's 4, it's 5, and I turn this into 5, 4, 3, 2, 1. I have just turned this hyperbolic, can't hardly graph it thing into a straight line. And now I can deal with the straight line. Is that exciting? It is very exciting. Okay. Now, most of what we're going to do in our world is not deal with base 10 or base 8. We're going to deal with base E. Not the television network. Okay? E is an irrational number like pi. It's 2.718, blah, 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 blah. All right? You're like, really? So we're going to write a lot of equations that look like this, or y equals a e to the RT. Okay? The cool thing about E, why we like E, is if we take e to the t, and we say, all right, let's take the derivative of e to the t with respect to t. It's not t e to the t minus 1. It's just e to the t. E is this magic number that is its own derivative. Okay? E is a magic number that is its own derivative. E is this magic number that is its own derivative. Now, let's look at this. Here's an amount. So let's say I start out with $1,000. Okay? I start out with $1,000. That's A. And I'm getting 5% interest for 10 years. That's R, and that's T. And you're like, oh, I might use this someday. Yes, you might. So Y would be $1,000 e to the 0.05 times 10. And if I calculate that out, I would get the value of A in the future. I'm getting the future value. And you're saying, well, I already know how to do that. We learned to do something in the old days like the sum of, we take x to the, 1 point, right? 1 plus r to the n, right? Yeah. So this is what we call discrete. If I get paid interest every month, that formula works. Okay? So this is discrete. This is I get paid every month, every year, every whatever time period it is, right? Or you can put a T up there if you like T. Okay? It's discrete. If, on the other hand, we're talking about the population of the Earth, the population of the Earth does not change discretely. All babies are not born on May 1st and June 1st and July 1st. There's continuous babies. Okay? So this, if I use this to try to figure out the growth of the population, it's going to be wrong. It's going to be too low. Instead, I use that, which is continuous. And this will give me a more accurate rendition of what's going on. Okay? And if you're saying, hey, really? Let's look at something. E is the following. E is the limit as m goes to infinity of 1 plus 1 over m to the m. Now you're like, eh? Okay. But there's some, just if I look at it on the surface, r is a 1 over, is a yeah. There's some parallelism there if you're paralleling your ism. Okay?